Okay, as I said, I'm gonna go over the slides. There are so many details about some mathematical derivations that you have it on the appendix of chapter 14. So I'm just going to mention most of the stuff, but the details about the mathematical derivations, I leave it for your information. You don't have to uh, memorize it or anything, but it's going to be for your information. So this topic again about big data. So what do you mean by big data? When you think about big data, it's actually simply large data set. Okay, so whether it's going to be like a large sample of people that you're collecting information about, a large time series, or it actually could be like a large number of x's, right? A large number of regressors that you have. Usually we have been working with about 5 to 7 regressors, but this topic, when I talk about big data, whether it's going to be like a large number of observations in terms of how many equations, but also it could be how many columns, which is how many x's. Um, so when we have big data, sometimes OLS is not the best estimation methodology. We would have to think about other options, okay, that can be used in order to filter for us the most important axes, the most important variables in the model that can be explaining the variation of our dependent variable. To do so, we have actually 3 ways. Okay, so we do have actually have more than 3 ways, but what we're going to cover in this topic is actually 3 ways. So ridge regression. For some reason, my pen is not working. Okay, one second. Okay, anyway, so we have the ridge regression. We have number 4, the lasso regression. We have the principal component analysis, and we have the application towards the end of this topic. And the summary is actually a very good summary because it takes you over the most important points. Okay, so as I just said, uh, big data could be many observations, and you think about observations in terms of the y, how many equations, or it could be in terms of how many variables. Okay, and by variables I mean the columns, which are the axes, and then it could be just other types of data that we haven't dealt with in this course, and it could be like a voice note, it could be an image, right? It could be as any other non-standard data type, could be a figure, it could be a graph, right? So these are called non-standard data because it's not like the regular numbers that we use to collect and analyze. But it's still important because it would give us like any information I can get about these people, about individuals, about the patients, about countries, whatever, whether this is like a text, whether this is an image, whether it's still called a part of the information, and it's going to be like an important information. Okay, I'm sorry, I can't still use my pen or even my fingers. I think it's a problem with my iPad. I have to restart my iPad, which I'm not going to do that now. Um, okay, so I hope that you guys are able to follow without me like writing on the slide. So when I talk about big data, okay, these are some of the things that you guys already know. So when you go to your computer and let's say you want to buy something from Home Depot, and you've been like thinking about this thing that you want to buy from Home Depot over the last 2-3 days, you see that this search is going to be like saved in your Google, right, or in your browsing history. So browsing history is a part of the information collected about your shopping behavior, right? When you go and you apply for a loan, then the bank is going to be collecting so much information about you. And not only that, and how likely, what's the probability of you repaying back your loan, Okay, so when I talk about these types of information, which we usually do not deal with, like we haven't dealt with browsing history, or we haven't dealt with images and text as information, these types are called nonlinear models and non-standard types of data. About iPhone, when you say facial or voice recognition, this is still an information that the machine is learning. Okay, the machine here is the iPhone, is learning about you. So this brings us to a very, very important terminology, which is called machine learning. What is a machine learning? Machine learning is simply what the computer, which is our machine, is able to learn about you, okay, using large data set or using large set of information about you. As I mentioned, like online shopping preferences, the computer is learning, right, from your browsing history, what you prefer, what you like to buy, and probably you will see it in the ads on the side of your email popping up, showing you the things that you have just searched. So this is called machine learning, okay? In econometrics, we usually call machine learning, but big data is just another terminology, but they both mean the same thing. So in this topic, or in this chapter, we will focus about this big data collection and how can I use it in order to predict the variations in Y or the variations in my dependent variable. Okay, so it's very, very important to understand the idea of the Ys, how many lines, how many rows I have, how many equations I have, how many people I have, how many patients, how many countries, and the set of columns, which is how many points of information, how many x's I have, how many columns of the matrix, of the X matrix I have. And this brings us to the relationship between K and N. Okay, K and N. K is the number of x's versus N is the number of observations, is the number of equations. At many times, it's not at many times, it's always the case that OLS will not be able to estimate for you a model when you have K is greater than N, when you have number of x's is greater than the number of equations. In this situation, you will not be able to use OLS. But we have other options, which we're going to talk about in this topic. As I said, that we have three ways of estimation, right? So let me take you back. So we said we have three ways I can estimate the model. I can use number three, which is the ridge regression, the lasso regression, the principal component analysis. The three actually are doing the same thing as OLS, which is estimating the variations of the dependent variable. Okay, but they just use different ways of doing so. So here in this model, we call it the predictive regression model because I'm using the x's to predict the variations in Y. Okay, so Y here is my dependent, is my predictor, and I'm using the x's to predict variations in Y. This is nothing new, right? We always use X and Y, X as regressors, Y as a predictor. And here I'm saying predictor and not an estimator because we're going to talk about out of sample. Okay, what is an out of sample? So I hate that I can't use my pen or my fingers to write because I was thinking I'm able to explain what is an out of sample using my pen, but it doesn't seem so. But the idea is as follows. So if I have, let's say, a data set from 1980 all the way to the year 2000, and I want to check how my model is good in predicting variations in Y. What I can do is I can use 50% of the data I have. So I'm going to use the data from 1980 to 1990 and stop there. Okay, so 1990 is my endpoint, and I'm going to take this endpoint, which is 1990, to predict 1991, and then predict 1992, and then predict 1993, keep going until, right, you finish the data set. I said 1980 to 2000 is my whole data set. I'm dividing it into half, so I'm gonna stop at the 90, taking the first 10 years to predict the next 10 years. Although it might be the case that I'm actually in 2020, I do already have the observations of the years from 1990 to 2000. But why I am predicting it? I'm predicting it because I need to see how well my model is performing. Because if my model is performing well, if my model is estimating close to the actual data of these years, of these 10 years, then I can be confident that I can use this model to predict actually the year 2021. Okay, so I have a model like y is a function of beta 1, x1, beta 2, x2, keep going, beta k, xk, and the error term. I don't have an intercept in this relation or in this model because, as you can read, it's deviated from the mean. So I'm taking y minus y bar, x minus x bar, x2 minus x bar, x3 minus x bar, and so on. So when I take the intercept minus its average, it's just like when I have an intercept which is constant, 5, 5, 5, 5 for 10 years. And what's the average of the 5, 5, 5, 5 for 10 years? It's just 5. So 5 minus 5 is gone. So that's why I don't have an intercept in this model. So I want you to understand that these capital letters y and x are deviations from the mean. Okay. So in the regression, which is 14.2, the line right under it is called the estimated population regression line. And as you can see, I don't have the error term because based on the OLS assumption, the expectation of the error given the x is 0. Okay, so here there is nothing new. I don't see anything new. Here, this part is new. So when I want to see how well my model is performing, I take my actual y and OOS is out of sample. Okay, so I have a model, as I mentioned, an example, 1980 to 2000. I'm going to divide it into half. So I'm going to take the data set from 1980 to 1990 to predict an out of sample part, which is all the points after 1990 to 2000. So why we call it out of sample? Because it's actually out of sample. What I have in sample is the part that I used in order to estimate my coefficients. I'm taking it in order to estimate each point, right, out of sample. So 1991, 1992, 1993, and so on. I can do it in one step, which is called multi-step forecast. So I'm going to take the coefficients and estimate all the future 9 years, or I can do one step ahead forecast. So I'm just predicting 1991 and that's it. And then I might be interested in 1992 and that's it and stop. Or I might be doing it one step ahead. So one step by one step by one step until you finish all your out of sample data, which ends in 2000, let's say. Any question? Guys, any question?
No, I'm good.
Okay. So, so what we have here is, again, every time we're using OLS, we're trying to minimize the sum of the squared mistakes. This is every time we're doing that. Now, I can also say it's the mean of the squared error. We have covered that before when we said the root mean squared error is just the square root of what you see here. So the mean squared prediction error is I'm taking the difference between my actual y, my estimated y. So this is going to be the error term. I square it up and I try to minimize it. So I want to minimize the sum of the squared errors. And since here I'm using out of sample forecast, then we're calling it OOS, just a notation. Okay. Danny, can you close the mic since you're not talking? Okay. So out of this model, we basically get my conditional expectation or the expectation of y given x, right? We do have the regular, the normal OLS assumptions that you already know, that I have kept repeating like every topic. So the OLS assumption that these set of observations are independent. I don't have multicollinearity problem. I don't have outliers, right? And the estimated error term given the set of x's is equal to 0. So there is nothing new. All the assumptions of OLS would still hold. Okay. There is a terminology which is called the oracle prediction. What's the oracle prediction? Oracle prediction is the best possible prediction. There is nothing new here, just the terminology, right? So the oracle prediction is just the best prediction. And I can think about a best prediction. Do you understand? Do you know what is a best prediction? Parth, do you know what is the best prediction? How can you define a best prediction?
I have a vague idea about it. The
Yeah.
best prediction, I don't have any.
Yeah, what do you think is the best prediction? Like, it doesn't have to be this topic, but in general, in econometrics, in foundation of econometrics, what is the best possible prediction? I need a predictor that
That closely relates to the result we are trying to get.
exactly. So in other words, you can say I need a predictor that minimizes the error term, right?
Yes.
Because if it minimizes the error term, I can guarantee that this gap, which is between the actual y and the estimated y, is at its minimum. So what you said is correct. So I want actually something, an actual, an estimated y that is as close as possible to the actual y, or in other words, minimizes the error term. So here in this topic, I want you to understand that when we talk about time series and forecasting, we usually have like a new terminologies. But when you think about these terminologies, there's nothing new. So oracle prediction is the best prediction is the one that minimizes the sum of the squared mistakes, or the one that minimizes the mean squared predicted errors. And that's it. Okay, so again, this slide is nothing new in terms of the methodology itself. It's nothing new. We've been like doing that all the time. The first line is simply the population regression line, in which I have the y as a function of the x's and the error term. And then the prediction, which has the hats, is the predicted population regression line. And then the predicted error, which is the third line, is just the difference, is just the gap between both. And every time you see beta 1, let's say minus beta hat 1, it's the amount of the bias, which I hope it's equal to 0, because if this is non-zero, then the gap between y and y hat is non-zero. And the higher the gap between beta 1 and beta hat 1, and beta 2 and beta hat 2, and keep going, beta k and beta hat k, the higher the gaps between these betas, the higher the bias, and the lower is my um, ability to predict or well predict the model. So we can combine this third line into a mean squared forecasted error, but just adding the square term and taking an expectation operator. And the details, you have it in your appendix of your textbook. We don't have to memorize it, but just if you want to understand how we were able to reach this line, just go to the appendix and read it. The most important thing about the mean squared predicted errors is that if I stop at the sigma and I don't have the addition part, then I just have the OLS mean squared errors, okay? Because the mean squared errors is equal to the sigma square u. But here I do have an additional term. This additional term is coming from the bias, from the distance, from the gap between my estimators and the actual estimators, or the population estimators. So when you think about it, you can actually think about the mean squared predicted errors of the OLS is simply equal to sigma squared u plus sigma squared u multiplied times k over n, which is the additional part, that if it is not equal to 0, then I would have an increase in the standard error coming from the increase in the bias or the distance between betas and their estimated betas. So our objective is still the same. I want to look for the estimator that minimizes the sum of the squared mistakes. So when I go back here, I want to find the set of estimators, beta 1, beta 2, or beta hat 1, beta hat 2, beta hat 3, all the way out to beta hat k, that minimizes the mean squared predicted errors. And it's actually a mathematical minimization problem. Okay, so we already know that we have this negative relationship between the bias and the efficiency of the estimator. Okay, so all the time I have this trade-off. If I'm trying to minimize the bias, the efficiency increases. And if I'm trying to reduce the efficiency, the bias increases, and so on. So every time I do have this kind of a trade-off. So we have a principle called the principle of shrinkage. What is the principle of shrinkage? So in 1950, there is a famous statistician. His name is James Stein, and he come up with this principle of shrinkage. And basically, according to this principle, is that if I have multiple x's, right? If I have x1, x2, x3, x100 that I can use in order to predict variations in y, I don't have to use them all, right? I can use a linear combination of these estimators such that I can maximize the explanation of the dependent variable. So how can we do that? So basically, and this is very important, which is the first bullet, when x's are uncorrelated. When I say that I have 100 variables that are able to explain y, if I'm assuming that these 100 variables are uncorrelated, then their correlation can be biased, or these estimators can be biased towards 0 or shrunk towards 0. Or I can write them in this form: beta hat JS, which stands for James Stein, which is James Stein is actually the last two names, the last name of two statisticians, James and Stein. And they created this shrunk coefficient, which is the C. And they basically said, okay, this C would be in between a 0 and 1, as long as I can assume that X is uncorrelated. And if this is the case, then the beta hat JS would be just a smaller than the beta hat, which is the actual beta. So the shrunk coefficient is C, and the shrunk coefficient would be a fraction, and that's why the beta hat JS would be a smaller version of the actual beta. So this slide, it talks about the trade-off that I just mentioned. So if I have this C, which goes from 0 to 1, and if this C gets smaller, as it gets smaller, the squared bias, what is the squared bias? Go back here. This is the squared bias, which is the squared bracket that you see here. The mean squared predicted error. We have everything in squared, we have like this square bracket, and then we have it to the power 2. So this is called the bias squared. So as the C gets smaller, as you keep shrinking and shrinking your model, minimizing and minimizing your betas, the squared bias of the estimator increases. And this is bad news, right? Because the bias would keep on increasing. But the good news is the variance would decrease. So every time I have a high bias, I have good news on the other side, which is a low variance or high efficiency. So I have to think about this trade-off. Would the increase in efficiency coming from the reduction in the bias would overcome the negative part, which is the negative effect, which is the bias, which is the increase in the bias? If yes, then just go for this shrinkage parameter. So Point number 3, it's saying that it says that this produces a bias variance trade-off. If K is large, the benefit of a smaller variance can beat out the cost of a larger bias. Okay, and this has to be like the right choice of C. So I would have like a multiple C's, and as you can see, the C goes in a range from 0 to 1. The smaller the C, the higher the bias, and the lower is the the variance. Okay, so when should I stop? When should I say this is the best C, this is the best shrinkage parameter? So how can we estimate this mean squared predicted errors? I have kind of mentioned it. I do have a sample of 10 years. Which part should I stop at and say, okay, this is my in sample, and which part should I say, okay, this is my part in which I'm going to predict? So the first option that you have is that you can just split the sample. What I mentioned is I split the sample half in sample, half out of sample. So if I do so, I estimate, I use 50% to estimate the other 50%, which as point 1 is saying, the estimate using half the estimation sample, use the estimated model to predict y of the other half. And then of the other half, I'm going to calculate the error. And I'm going to use this error to go to number 3 and compute the mean squared errors. Or you can add the mean squared predicted errors. The P here is just a notation telling us that it's a prediction. Okay. And this is just by splitting half-half. But however, in real life, it's not recommended that you would split half-half. Like, why should I be using 50% only of my data set to predict the other 50? It would be much better to increase my set of observations and just predict few points towards the end. As we have been always saying, it's much better to have a larger set of observations. So this methodology, which is called the M-fold cross validation, is instead of using 50-50, no, use 90% of your data and predict 10%. This is just like the author choice. For example, I was like writing a forecasting paper, and in the forecasting paper, I used what's commonly used in the literature, which is I use 75% of my data in order to predict the last 25%. So it's up to the author, but the most important thing to remember is that you actually need to maximize the in-sample number of observations as much as you can. Okay, so it's using 50-50 is not optimal. Using 90-10 is fine, but for me, I prefer to use 75-25. So number 1, we're saying that, okay, according to the M-fold, you're using 90-10, 90% of the data to predict 10%. You're going to use the data to predict the 9 possible subsamples, okay, without any overlaps. So I'm predicting I have a data from 1990 to 2000. I keep repeating the same years, okay? So from 1980 to 2000, 20 years. I'm going to split them, let's say 50-50. So I'm going to stop at the year 1990. I'm going to predict 1991, 1992, 1993, and so on. Okay. If I'm using, let's say, 20 years and I'm using 90% of the data, I'm going to stop at year number 18 and I'll be predicting, right, the last 2. So 90% of the 20 years is going to be 18 years. So I'm going to be using 18 years to predict 10%. 10% of the 20 is the last 2 years of the data set. Okay. So this graph is showing us a presentation of the sum of the squared residuals, which is the one of the OLS. There is nothing new about the blue line. Okay, this is something that we know already. The penalty is the penalty coming from estimating, oh wait, I missed one slide. So wait, just want to make sure. Yes, I missed, I skipped the slide. So the ridge regression, is like James Stein, the same idea, which is I'm trying to minimize the sum of the squared predicted errors, okay, by using a shrinkage coefficient. So here I have the lambda ridge. So the lambda ridge is called the penalty term because every time you are adding a new coefficient, the standard error is going to increase. So in order to see how they are correlated, you look here, the blue line is the sum of the squared residuals of the OLS estimator, which we know already. The OLS doesn't have any penalty parameter. Like if you go back here and you remove the lambda, if lambda is 0, which is the additional part, if the lambda is 0, then I go back to my OLS standard error, or I mean like the variance. So here some of the squared residuals. So here I see the blue one is the one without the additional part. But if I add the penalty, then I'm going to come to the line S ridge. And if you want to just graph the penalty, it's going to be like penalty B. The penalties, the SSR, the S ridge, they all depend on beta. Okay, the value of the estimator. As you keep increasing betas, the SSR would keep on decreasing, but at a certain point, it would start to increase. So it's a nonlinear. Same goes with the S ridge. So my question would be, okay, when can I stop? Like what is the optimal value of the beta? The optimal value of the beta is the one that minimizes the line, right? Which is the one on the minimum point of the line. So as you can see, the beta hat ridge is smaller than the beta hat under OLS. And this makes sense because the beta ridge has a penalty attached. So it makes sense that you have to stop earlier than the OLS because the OLS doesn't have any penalty coefficient attached to it. Okay, and that's why I have the beta hat ridge is smaller because it has a coefficient or a penalty coefficient attached to it, which makes the person like stop earlier because the more that you go, the higher and higher and higher it increases, as you can see, at a much higher rate than the SSR. Any question?
No.
Okay. So again, so this slide is just saying what I was saying, which is I'm trying to minimize the mean square predicted errors such that I can choose the delta ridge, right, that minimizes, or the lowest point that minimizes the amount of errors I have in the model. So let's say if I have the data set on the school level test scores, and we're talking about big data. So let's say I have 3,932 observations, and this is from the actual from an actual data set on California Elementary District school data. And if I using 50% of the data to predict the other 50, then you split this 3,932 into two groups, use the 1,966 to predict the other 1,966. So this is like half-half splitting. Okay, this data set has 817 predictors, as we're gonna see. So what are the 817? We're talking about big data. And whenever I talk about big data, it's not only how many observations I have, but also how many X's I have. I want you to look at this table and understand that all these are X's. All these are regressors. Okay, so I have mean variables of 38 X's. Add to that the squared of the mean variables, another 38 variables. And then I'm gonna also add the cubes of the mean variables, another 38 variables. And then I'm gonna also have interactions of the mean variables. So you have also interactions. So the interactions would add 703 additional variables. Can you think about how many all these? So it's 38 plus 38 plus 38 plus 703, 817 number of predictors or x's. Can you imagine? Like 817 x's you have in the model that you're actually trying to see whether all these make sense to you or not, whether all these are needed or not. As we're going to see, some of these estimation methodologies would just remove some of the access for you. They would tell you, okay, I don't need this, I don't need this, remove, remove, remove. They don't explain much of the variation, so you keep on removing, removing until you end up probably by 56 instead of the 870. We're going to see that. Okay, so in this figure, we have the square root of the mean square predicted errors. If you still remember, it is called the root mean squared errors. And since I have prediction in this topic, so we call it the root mean squared predicted errors. And the idea is simple. I do have the root mean squared error keep changing with the penalty parameter. What is the best penalty parameter that I can use to minimize the amount of errors? And in this figure is just trying different numbers for the penalty parameter. And we came up here with lambda hat ridge as 2233 as a point which minimizes the amount of errors. And this would give us, so when you go here, of course I can't show you with my pen because it's not working. Let me try again. Unfortunately, nothing. Okay. This is my first time not to check my pen before I start the lecture. Okay, I shouldn't do that again. Okay, so as you can see from this blue U shape, that the penalty parameter is 2233, and it's with about 39.5 mean squared forecasted error. And what you have here on the left, OLS root mean squared errors is 78.2, but the one which is coming from the ridge estimation methodology is 39.5. Which one is better, do you think? Which one is the 78.2 or the 39.5?
Is there 17.2?
So remember, this is an amount of error. So if I'm asking you which is better, you would need to look at the one that has a lower error. Right? You get that?
So 17.2 is the relevant one.
17.2, where's 17.2? We have 78.2 and we have 39.5.
Oh, I thought you said 17.2.
Oh, no. So we have actually the two numbers that I'm saying, I'm just reading the slide. So what you have is 78.2 and 39.5. So if I'm saying which one is lower, then of course the ridge is a better predictor as compared to OLS. Any question here? The other option we have is called the lasso estimator. What is the lasso estimator? It's just doing the same thing that we just mentioned with the ridge regression, which is, again, I'm trying to find the lambda or the penalty parameter that minimizes the root mean squared predicted errors. And but this time, as you can see, the penalty parameter is multiplied times the sum of the absolute values of the betas. And this is different from the other one. Let me go back and show it to you. The other one was the lambda is multiplied times the sum of the squared of betas, right? So this is the main difference between the two. So again, we're going to go into the same idea, but here with the lasso, it has one thing that is different. So with the lasso estimator, lasso estimator does not only shrink the value of the beta, but it also discards the x's that you don't need in the model. It would plug a value of 0 to the coefficient of these x's. So it's different in this way. It's not only going to give us a smaller weight to the coefficient, no, it's going to give a 0 weight. So these coefficients are not actually there. Okay, for some reason, I have here two graphs that do not show up. So see that, like when I go there, you will see it and it's gonna disappear in a less than a sec. See, I have no idea what's going on. When I do it this way, I can see it here. See, it's right there. Okay, so what I want you to do is, if you have it, if you have your slides, just look at the graph and or the two graphs, because I can't open it on my iPad for some reason. But on this graph, it is actually taking again the OLS, some of the squared residuals, and the ridge, some of the squared residuals, and the lasso, some of the squared residuals. And it's showing you that the lasso estimators can shrink the coefficient all the way to 0. Okay, the estimator can be actually 0. And that means the beta can be exactly 0. And in case one of the axes is not that important out of the 817 axes, some of them are not important, then these unimportant regressors would be shrunk to 0. And this is actually an advantage, right? It's not like I'm gonna have like multiple coefficients with a small weight. No, I'm not, I really don't need them. And that brings us to the name that is given to the lasso estimation, which is called the least absolute selection and shrinkage operator. That's why it's called lasso. So the least absolute selection shrinkage operator. And this one is, as I said, it's the best when you have so many predictors that are irrelevant. Using lasso would just take care of these coefficients by just removing them for you and just attaching a 0 value for them. Okay. The models in which most of the true betas are 0 are called sparse. Okay, so what is a sparse model? Sparse model is a model that you have most of the betas are 0. Again, this lasso estimation methodology works best when you have so many predictors that are irrelevant, okay, because it would just like remove. But it has a disadvantage. The disadvantage is it's very sensitive to how you are estimating your coefficients. I mean, your variables, I'm sorry. So if I have dummy variables about freshmen, sophomores, and juniors, and you're omitting seniors to avoid the dummy variable trap, and you re-estimated the model by using a continuous instead of the dummy variable, right? By saying, for example, freshman is less or equal to 1 year, sophomore is less or equal to 2 years, junior is less, and so on. The lasso estimation methodology is very sensitive to the unit of measurement of the variables. So if the variable is dummy versus continuous, then you might get different results. So this is one of the disadvantages of the lasso estimation, and it's known, but in case someone is using it, you would see that they are mentioning this disadvantage. All right. So the application of using the lasso estimation methodology on the school level test scores, what you can see again is a U shape. What we're looking for is the same. I'm looking for a penalty parameter that minimizes the square root of the mean squared predicted errors. And this happens to be the value at 4,527 lambda, which corresponds to the value on the y-axis, which is the square root mean predicted error of 39.7. Again, comparing the OLS 78.2 versus the 39, definitely the lasso estimator is better because I have less amount of square root mean predicted errors. What we have left is the third way of shrinking parameters. And this is actually the one that I prefer to use in most of my papers when I do have multiple variables talking about the same thing, and I really want to use, I really don't want to use them all. I want to shrink them into one variable or into a summary variable. One of the famous uh, ways, or one of the famous, I should say, variables that we use a principal component for is called the governance variable. The governance is a variable that combines a corruption in a certain country, the bureaucracy, the law and order, the transparency, the voice of people and accountability, and so on. So it combines about 5 or 6 variables. If someone is interested in working with governance without going into the details of governance, without going into the details or without adding the 6 variables of governance, you can just create a one variable that combines them all into one variable, or creating a linear combination of all into just one variable, and you call it governance. So principal component, it's doing so, combining or shrinking the number of x's into just one x, or into a principal component. The idea is here, so what if I do have x1 and x2? So let's say x1 is corruption and x2 is rule of law. And you really want to use both of them to create one variable. So what you need actually to do, or what principal component is doing in the background of stata, is maximizing the variance of the linear combination of ax1 plus bx2 subject to a squared plus b squared equal 1. So out of that, you get this figure in which you're trying to get a principal component 1 and a principal component 2, and you can just write it in a simple form, like a more general form in terms of the J's principal component by, if I have, instead of just x1 and x2, I have multiple x's, I have k x's, and I have k linear combinations, then, and I have PC1, principal component 1 and 2 and 3 and 4, all the way up to j minus 1. Then I can write their maximization problem in this way. So I want to create a principal component of this linear combination that takes or absorbs all these variations in the x's as much as possible. So this is, I mentioned most of that. So it's kind of a compression tool used to reduce the very large data set into a small one. And I told you that I have been using this a lot in my research, because there are at many points variables that represent different dimensions of an economy. I want to put them into one variable, let's say like governance. There is also the digitalization index, which we have a digitalization of household, of production, of infrastructure, of the government, and so on. You want to put them into just one digitalization index, so you would combine them using the principal component analysis. And the command in stata is really easy. So you just type PCA, and then you type x1, x2, x3. So let's say PCA, corruption, rule of law, accountability. And this would create for you, and with the data set, a list of additional variable, one additional variable in the list of your variables. That would be the principal component. And you would be generating or giving it a name. This is an example telling us that a familiar example is image compression. So what the principal component is doing a compression of the variables. And this is similar to the compression of an image, right? What you do when you compress an image, you retain the main feature of the image, right? But you want to reduce the file size. That's the same idea. When you look at the fraction of total variance explained, of course, you want to maximize the variation explained, right? Which is the R square. What you can see here is a principal component number. If principal component 1 would explain 18% of the variation, principal component 2 would explain about less than, maybe like around 11% of the variation, and keep going. The higher and higher, or the more and more number of principal components, the less the explanation of the model. Okay, so this is called a scree plot. Scree plot is just the plot that shows the relationship between the principal component number and the explanation of the variations in the dependent variable. Okay, so how many principal components? We actually going to be like doing the maximization problem that I showed you, and this would answer for you how many p's. For example, here, when you look at how many p's, or what is the value of p, I should say, again, you're doing the same thing. You're trying to minimize the square root of the mean square predicted errors subject to the principal component number. And here, what we got is the p hat, the linear combination that minimizes this squared root mean error is equal to 46, which corresponds to 39.7 as a principal component. Again, much smaller than the OLS. Okay. All right. So the last part of this topic is just an application. So again, we're using the school test scores, and we have different sets of predictors. We have a small set, which just I have 4 X's. We have a large set in which we have the 817 that I just showed you, where you have like quadratic, cubic, interaction, mean variables, all sum up to 817. And you actually might have additional variables that can bring the number of observation and the number of X's to 2065. And this very last one, which we call the very large data set, the number of K, the number of X is much higher than the number of observations. And that's a point in which the OLS cannot be estimated. You cannot estimate. So this is a summary of the results. Again, this table is divided into small, where you have just 4 X's, large, where you have 817, very large, where you have 2065, and you can see the very last circle, or the very last oval shape doesn't have an estimation, because the OLS cannot be estimated when the number of K's is greater than the number of N. Okay. When you look at the out of sample for the mean squared forecasted error for the OLS using small versus large, as you can see, using small, I have a smaller amount of error. The out of sample root mean square predicted error is small. It's 52.9 versus 64.4. So definitely, as you can see from this box, OLS gets worse with more predictors. And we can't even estimate it when I have the K greater than N in the very last, or towards the end of the table. Okay, one way to estimate whether my estimator is performing well is to compare my standard error for the in sample versus the out of sample. If I don't see large variation, then you're doing fine. So what you can see here is for the OLS, in the small sample, I don't have big variation between 53.6 and 52.9. So OLS is doing fine with a small sample. When I jump to the large sample, I can see a deviation between the 78.2, 64.4. So the amount of variation gets wider. So the OLS is not performing really well. Look at the ridge, the lasso, and the principal component. They are similar results where the root mean squared error is almost doesn't change much. So 39.5 versus 38.9, it's very, very close. 39.7, 39.1, again close. 39.7, 39.5 is again close. So what we can tell is the computation of the root mean squared error for the ridge and the lasso on the principal component is much better than using OLS for the large sample. Next, okay, this is what I already mentioned. So those 3 have big improvements over OLS, nothing new. What else? Yeah, ridge has a very slight edge, because as you can see, it is the smallest, 38.9 versus 39.1. Really, in practice, I don't see a huge difference. It would be like up to the author preference. But yeah, in terms of the numbers, yes, it's the smallest. When you look for the very large sample, as you can see, we don't see a huge difference in the standard error, right? So there is no much gain. So I was expecting that with a large sample, I would see a smaller variance or a smaller out of sample root mean square predicted errors. But really, I don't see a difference, right? Or a much difference. It's actually the same for the lasso estimation. It's slightly 0.1 higher for the ridge, and it's actually again 0.1 higher for the principal component. So we don't see a much gain. This is not always the case, like it's not a rule. Usually you would see a gain, but here in this model, if you're estimating this model, your conclusion would be, okay, I don't have to go with a very large sample. A large sample would be enough because I'm not gaining any reduction in the standard error going from a large to a very large or a big data analysis. Okay. Okay, so this one is just showing us the prediction, okay, made by Ridge and Lasso, and the principal component. Okay, so as you can see, you have a correlation, positive correlation. Whatever you get with the Ridge prediction would be very close to what you get with the Lasso prediction. Okay, and same with the principal components. So there is a kind of correlation between the results of the three methodology, but with the OLS, it's going to be like totally different. It's going to be like the worst, as we have seen in terms of the OLS. I like this summary very much because it goes over the most important points. So we said that with many predictors, the OLS would perform the poorest as compared to the other three methodologies for the out of sample predictions. We need to have the correct amount of bias or the shrinkage parameter, okay? Because I want to create this trade-off between the bias. I'm going to accept a high bias if you give me low variance, okay, or high efficiency. So the high bias would offset the low variance. With the ridge and the lasso estimation, this shrinkage parameter can actually go all the way to zero by eliminating regressors that are not important, which is great. Remember, the lasso has a disadvantage of being very sensitive to the choice of the unit of measurement, dummy versus continuous, so you might get different results. So you have to be very careful using it. The principal component collapses, right? The x's into fewer number of x's, making your life easy, right? Making your life much easier in terms of creating a summary of a set of, let's say, 6 variables into just one variable, okay? So again, it's has advantage over the OLS. All right, guys, so I'm gonna stop here. As I said, I have to go because I have a meeting, and in any case, we don't have any practice for this week because we're not actually gonna be working with large data set. Your Stata version will not accept any larger data set of this amount of observations, but this topic is for your own learnings. And also, if you see a question on it on a homework or on the final exam, would be like more of a descriptive, like asking you questions that are not quantitative. So you do not expect a Stata question on this topic. All right, so any question? Dan, Part, any question?
No, I'm good. It's
Yeah, same
can I
here.
send you a question about?
Yes, you want to send me a question about what? Dan, I can't hear you.
I said I'm gonna just do the practice, and if I don't know something, can I like ask you?
Great, yes. For last week, time series is very important, and you guys should expect to see questions or part of questions in the final, or even like in today's assignment. So it's very, very important to do the practice of last week, the stata and the non-stata version. And I would advise you to watch all the videos before you start. And the good news is the stata video or the video on the stata is very related to the practice. So just watch it first and then replicate it. Okay? All right, guys. So I'll see you next week.